big picture. It's been a while. As I already said in Twitter or something, um, I'm kind of becoming a father, second time father, I'd say, really soon. And so, things will naturally slow down a little bit, and you'll see this in the next weeks. I'll be uploading less and less, but I'll still keep trying to do my best to be consistent with these. It's sort of a long term learning project anyway, right? But just so you know, probably around October, November, we'll kind of be back a bit more full steam on these. And the thing is, kind of like just to recap a little bit where I left it last week, or where are we going really? So we're trying to understand, the whole goal of the project is to learn kind of quantum mechanics from scratch. Really kind of like using something a bit of an unusual approach, right? So with Wolfram's, just kind of taking Wolfram's physics project, and trying to understand how they're trying to model quantum mechanics, and then therefore just learning quantum mechanics, right? So, and of course that's challenging because their model and approach might be wrong, but it's kind of a bit of a feels a bit more like a fundamental approach, like you're kind of trying to discover things rather than just like reading through the textbook. Although a lot of the times I'll just kind of be going through textbooks and whatnot. But anyway, I think one of the things that one of the things that I did not fully understand from Wolfram's model is how do they define entanglement. Because they do it in a weird way where you have this multi-way system, that is kind of like branching out as you evolve your quantum system. And so different states at a given point in time that share a parent, they basically say that's entanglement, right? And which is was really confusing to me because from a more traditional quantum computing sense or point of view, you define entanglement as like the correlations between subsystems rather than just, sure, it's a correlations in terms of states, right? Like you can say this state is correlated to this state. um, but like entanglement, that's the way that I've seen it defined, which seems to be a bit contradicting here. So in a way, because I feel they're trying to map their model to the path integral model, um, there just might be a change in thinking that is needed there to try to understand entanglement from the perspective. So I kind of set out to understand entanglement from a path integral perspective. But before I approach the path integral, just kind of wanted to go through the very basics of, let's understand Schrodinger's equation. How does these, because the Schrodinger's equation is a bit more of the, kind of the operational perspective, right? Like the operators model, where you kind of have like a state and you apply operators and you evolve the state. And that equation kind of tells you these, right? It tells you, it basically kind of relates the wave function, the energy, and sort of, the energy as being the operator, I guess. And so I know that there is an equivalence between the Schrodinger's equation and the path integral model. And that's kind of, I'd say, my next big step. I just want to dig a little bit deeper first, do some, low-level examples, and just going through the basics of, saying, the quantum harmonic oscillator. Now I'm going to take a look at the particle in the box model because I think that's even simpler, just to kind of try to understand or go through example on how is Schrodinger's equation solved, and sort of its more simplistic ways, right? And I'm not going to go too much into detail, I guess, but I do want to get better at differential equations, that a lot of the kind of like low level skills that you need to even just think about these problems. And I'll try to see if I can carve some more time to do a bit more drilling in that and actually really go through just like differential equation exercises and things like these. But that's going to take a bit until I get the time to do that. So for now, I'm going to take a look at this example, which seems to kind of walk you through the particle in the box setup, and then it actually goes step by step and solves the Schrodinger equation. So I'm going to take a look at these, and I think I really haven't read through these in detail. And then there's some questions at the end. Um, yeah, so basically that's kind of what I wanted to take a look at today. And I guess what we'll do next is we will kind of start walking towards the sort of the path integral equivalence, right? And how do we go from the Schrodinger equation to the path integral, and then see how can we understand entanglement from the path integral's perspective. That was kind of my my goal there, to be honest. And in the meantime, I'll try to kind of keep doing exercises and whatnot. So let's go. Um, and as I said, here I'll just be, this is going to be a bit more of a layback stream where I just kind of go and read, but I'll try to understand each step. So let's see. Um, a particle in a one-dimensional box is a fundamental quantum system, quantum mechanical approximation describing the translation motion of a single particle, whatever. Yeah. So the idea is just a very simple model. And I guess the idea, like based on what I've seen online, this is, you kind of define a system that has got two boundaries with infinite potential. The only reason you define this infinite potential here is just to kind of have boundary conditions, kind of like limit the system. And like this is just something to enforce that the particle cannot be found in the regions past these points, 0 and L, right? Um, Horizontally in an infinitely deep well from which you cannot escape, the solutions to the problem give possible values of E and psi that the particle can possess. E represents the allowed energy, and psi of x is the wave function, which, when squared, gives the probability of locating the particle in a certain position. Cool. So to solve the problem, you go through this recipe, right? Which is define the potential energy, solve the Schrodinger equation, define the wave function, and then define the allowed energies, which is kind of more or less what I expected. Cool. So how do you go about this? How do you define the potential energy here? Um, well, isn't the potential energy constant? I guess it should be constant, right? Because if it were not constant, then it means that you would actually, yeah, I don't know. The potential energy is 0. Yeah, okay. So, oops, sorry. What is this? The potential energy is 0 inside the box. So, and goes to infinity at the walls of the box. Okay, we assume the walls have infinite potential energy to ensure that the particle has 0 probability of being at the walls or outside the box. Doing so significantly simplifies our later mathematical calculations as we employ these boundary conditions to solve the Schrodinger equation. But it's going to have some, if it's moving, it's going to have some kinetic energy, right? It just doesn't have any potential energy. This means it just cannot, like, doesn't escape. So if this is only kinetic energy, this energy is kind of constant. So that means my guess would be this is just going to be like you're gonna have a move, like this is going to just move like that, like the arrows say, right? So like left, right, left, right. So let's take a look at the time-dependent Schrodinger equation, time-independent, for a particle of mass m moving in one direction with energy E. So this is kind of the first challenge, right? It's always like, what Schrodinger equation are you going to use at all? Like, I guess that's kind of where a lot of the, um, you got to get that right? Because there's just a lot of varieties of these. There's time-dependent, time-independent, and then there's like a whole bunch of like, is it psi, is it that you're doing it like from a position perspective, from a potential perspective? Like, so what is this saying? So this is saying, that's just the basic stuff. So I guess that's the energy. You see that's a very confusing. It's like, when do we use E? When do we use H? And why is this multiplying? Yeah, okay, no, that's okay. So is it? Yeah, yeah. So here just the psi of x and t is kind of factored out, but essentially that's it. So you have the potential and then you have the kinetic energy. I still I still don't know where that comes from, and I guess this is different if you take a look at potential, at momentum or at position. But essentially that's this, right? So h bar squared divided by 2m, so minus, and then times the second derivative of the wave function with respect to x. And then there's the potential. And that gives you the energy operator. So h is the reduced Planck constant, m is the mass of the particle, psi is a stationary time-independent wave function, this is the potential, and E is the energy, a real number. Is it a real number? Oh yeah, but then why? So what is this H in here, right? I thought that was an operator. Oh, that is the, okay, so that is the H is then what you replace for all this kind of stuff, I guess. That is confusing. Or is it that, okay, so is it that it's just saying that's the energy, that bit is the energy. So we're keeping that part of the equation out so far. So, Batman. Sorry, gonna be coughing quite a while. Cool. So the equation can be modified for a particle of mass m free to move parallel to the x-axis with zero potential energy, resulting in the quantum mechanical description of the free motion in one dimension. So I guess what you do here is just say potential is zero all over the place, so we're just left with these. That's understood. Okay, and now we go and say, cool, this equation has been well studied. It gives a general. Okay, so that's the general solution. But that's not what I want to know. I want to know, okay, so how do we solve these, right? So define the wave function. And I think that's the point, right? So that's what I said, that I think most of these Schrodinger equations are exercises are solved because you kind of know more or less the shape the wave function is going to have. You just don't know what the concrete parameters of the function or concrete constants of the function are, the characteristics. So the solution to this we found above is a general solution for a one-dimensional system. We now need to apply our boundary conditions to find the solution to our particular system. According to our boundary conditions, the probability of finding the particle at x0 or xl is 0. So when x equals 0, sine of 0 is 0, and cosine of 0 is 1. Therefore, b must be equal to 0. Oh, that is the general shape. That is the general shape of psi. But how you would get to that, I don't know. So it just says it's been well studied, and that's the general solution of psi. So here, what they're just saying is that we applied boundary conditions. So when x equals 0, sine of 0 is 0, and cosine of 0 is 1. And so therefore b must be equal to 0, right? Because otherwise the boundary conditions wouldn't be fulfilled. So this kind of leaves us with these even more simplified shape. We can now solve for our constants a and k systematically to define the wave function. Okay, so how do we do these? I guess just by substitution, right? So this is here, so we can do the second derivative of these. So solving for k, so differentiate the wave function with respect to x, then do it a second time, and then since psi of x is a times sine of kx, right? Then the second derivative. Okay. So that is okay. So that is the okay. So you can replace the derivative for these in the main equation of psi, right? Of x, I guess. If we then solve for k by comparing with the Schrodinger equation above, so then you have the Schrodinger equation here where you can have the Planck constant, the reduced Planck constant is h bar squared minus h, and then here it's just basically minus k squared times psi, right? How do you do that? So if then we solve for k by comparing with the Schrodinger equation above, we find that k equals to these. How do you solve by k in this case? Oh, okay, so that actually you include, yeah, you just basically, so you just basically replace these here, then the wave function disappears, right? Because you can cancel it, it's on both sides. And so you're left, like, let's see, let's just take let's take paint here. I still haven't got my pen to work correctly, right? But you have I? It's not working. The pen's not working. Oh, it's actually working. Let's see how well this works. So you have h bar squared 2 times m, and then you replace that whole thing for like minus k squared times psi, right? Equals e times psi. And so I guess these psi's kind of go out, right? And so then you kind of have minus k squared equals e times, 2m, and so there's a negative sign here, but we can cancel those. And then, if you do the square root here, the square root there, so you kind of have k equals the square root of 2 pi. What the fuck? What am I missing? I'm missing something. Why 8 pi squared me? Like I have 2me divided by, but why 8 times pi squared? I don't know. Am I missing something? Am I missing something? I'm definitely missing something. Or that's just wrong. It's 2m. And here's just this 8 pi squared. Okay, I don't know. We can take a look at another example. But now we plug k into our wave function. Cool. And now, now we can actually replace this whole thing in the original Schrodinger equation. So in run A, we have to apply the boundary conditions again. Recall probability of funding 0. So when x equals L, so here we can actually find, but where's x in here? Oh, here. What? I'm so confused. What is this x doing here? I think there's missing a parenthesis here, right? It's like the whole thing is part of the sign, I think. Because kx, and so we just replace k. I think this missing a parenthesis. I think the whole thing is just part of sinus. And so, and then if this whole thing is 0, and we know a is not 0, then it means that this whole thing here must be equal to n pi. This is only true where n equals 1, 2, 3, etc. Then to determine A, recall that the total probability of finding a particle inside the box is 1, meaning that there's no probability of it being outside the box. When we find the probability and set it equal to 1, we're normalizing the wave function. So if you're integrating the wave function square y square. Oh yeah, because if we square the wave function, then we get the probabilities. So if we square the wave function, we integrate it on the in the boundary conditions, we know it's 1. And so that allows us to find what? Okay, to find the constant A. And so now we know that we know the wave function with respect to like L. And then you can find the allowed energy values. This N. So, okay, so there's a couple of steps here I don't get. The first one is this one. So where is this 8 pi squared coming from? Sorry, here, this one. And the second one is how do they do these here? So they say if, what's the one x? So when x is, you're not really solving for A, are you here? Yeah, okay, you're solving for A. That's the whole thing. So the first thing you're doing is you're taking that. So now we have a wave function in terms of energy, and then yeah. And so now we know the boundary condition, so we can say that when x equals L, we know that this whole thing is 0. And so for the function, okay, so yeah. So if I could look at the sinus function, right? So if we take a look at a sinus function, it's only 0. It's only 0 in kind of multiples of pi, right? Yeah. So that's what you're using here. So you're saying this is only going to be 0 in multiples of pi. So this whole block here. Oh God. So this whole block here is only 0 for like pi, like n times pi, n being just like natural numbers, right? Well, to be honest, 0 would also be correct, would it? So what? So how do you plug this back? So how do you plug this back? Plugging this back in where? Sinus. Are we just saying that is then just a constant or something? Like, so the wave function, this is also a bit tricky. So what is it that they're doing here? So psi equals A times sinus of n pi divided by L. Why? If I take the L and put it here, why? Oh, okay. So then we're saying, of course, that this whole thing is n pi divided by L. So we plug it in back here. Yeah, makes sense. So we plug it in back here. So it's a bit confusing because it says solving for A, but then you start kind of, first of all, solving for, yeah, just simplifying the wave function because you have that the boundary conditions, and so kind of expressing it. Okay, so you express it always as a function of L in this case. It's interesting, and then you have the wave function, the wave function like that, and then how do you find A? Well, the next thing you know, so you know that so you know that to determine the probability of the box, and you can do these things. So you go through these, and then you get like yeah, that's I guess a basic integral thing, right? Where you just So that's a times sinus of n pi divided by L x, and so you kind of take the, and that's all squared, so you take the constant outside of the integral, and then you keep these here, and that's then, so the using the solution from an integral table. Yeah, I guess that's taken from an integral table, which I don't know. This one of these canned solutions, I guess. Oh, there's an actual page called integral minus table. Yeah, that's cool. That's cool. Okay. Basic forms. Interesting. With roots, integral with logarithms, with exponentials, with trigonometric functions. Okay, so you have the integral of squared sinus is just yeah, okay. Yeah, but I think here you have to kind of, isn't it that you when you have like the intervals, isn't it that you kind of have to do the integral where x is 0 and then do it when x is L and then kind of minus or something? I think there's something like that, right? So I think there's a way you solve these. There's a particular way you solve these cases, these functions, these integrals. Yeah, with a minus or something. Definite integrals. Oh, they're called definite integrals. Definite integrals. Yeah. So 5 easy rules for definite integrals. So so this was applied, right? And then what? Okay, so it's like, yeah, so it's like you can have an in-between step or whatnot. I guess you can just replace this at the end, right? So you can just say a square. So you get the, I'm kind of lost. I thought there was a clear method for these where you just kind of take one of the boundaries and then another one, and then you, because this is x divided by 2 and then minus sinus of 2x divided by 4, because remember a is 1 in this case, right? So this is the equation 72. The, this is something that I have to kind of work through. But yeah, so you solve these and then you get a is that, right? I mean, how would you solve that? That's basic stuff. It just bothers me now. As an assertion, this integral from an integral table, we find our normalization constant, a square root of 2 divided by L, which results in the normalized wave function for particle. So we've basically found the wave function. And if you plug in this wave function, then you can solve for E, which then these are the allowed values of E. So we'll go, because we're done. So we'll just go through these now in a second. So we cannot. So where is paint? Where's paint? Where's paint? So we have a squared. No, so we have these thing here. Sine the square of like n pi x divided by L, right? Dx. And so how do we solve this portion here is we okay, so we have that thing where a is like n times pi divided by L, right? So if I use the table in here, it's telling me I have like x, so x divided by 2 minus sinus 2ax. So this means I need to like do so x divided by 2 minus sinus of like of 2 times n pi L x, right? And so divided by 4 times this whole a, which is like n times pi divided by L. So this is the result of that thing. And we know that a times these, a squared times these equals to 1, right? And now we solve for a, basically saying that, a equals to 4n pi divided by L, this whole thing kind of divided by this whole beast here, right? So x divided by 2 minus sine of 2n pi Lx. How do I simplify that? What is this? This is going to be something like 2n divided by... Oh, well, I know what L is, right? I know that L... Do I know L? No, I don't know L. So, okay, it's a multiple of pi. Yeah, cool. Like, so if n, so we know that n takes values like 1, 2, and 3, etc., right? So this means that it's always going to be, I don't know what L is, right? But if it's, this L bothers me a little bit because we don't know what L is. But oh yeah, so that's square, right? So obviously that's the square root. That's where square root is coming from the solution. And kind of like my assumption here will be that then you kind of just... Oh, and here's where I'm missing. Okay, so here's where I should kind of use these things, the zeros, right? Because we know when x is 0, so when x is 0, we know that this is 0, and then we know that sinus of the sinus of 0 is 0, right? So So then this, no, but then this whole thing would be undefined. Mm. How do you solve these definite things? That's what I'm missing. I don't like. How do I know? Oh, so I know. I mean, I know the solution is one, right? So isn't it that you kind of plug in? So plug in zero, right? And then plug in n, plug in l, and then you kind of that minus that equals one or something like this. Uh, that's what's bothering me, that I don't know how to solve these definite things. And it's just probably something very, oh, look at this. Ah, so it's f, okay, so is f of b minus f of a. It's that simple. Ah. It's f of b minus f. Oh, what is f though? Is it the integral? The integrated, so you integrate that, then you replace, yeah, that's what I thought. I think that's what it is. So you kind of say, you know, like forget these, right? So if this is the, so if this is the current integral solution, now you do, what's that? So b is the top minus the bottom. So the end minus the beginning. So you do the n is L. So you replace x for L, right? And if you do that, then you have a, then you basically have a sinus of 2 times n pi, which is basically, again, it's always 0, right? So when you do L, the whole sinus thing is 0. So you kind of have, then you have, these thing where you can apply that, um, so that's L divided by 2 then. Uh, how was that? How did that work? I think you're, I think, yeah, I think that's basically, yeah, it's the same like multiplying. So this stays at the bottom. So you kind of have 2 times 4n times pi divided by L squared. Could it be? Something's off here. But yeah, okay, divided by L squared. So that's what you have if you plug in L. If you plug in 0, well, basically I have 0 here minus, and then sinus, so sinus 0 is 0, right? Isn't it? Yeah, but that's weird, because then it would mean that that's undefined, because it's d divided, you just not divide by 0 unless you, mm, mm. And I don't know how to get rid of the n, to be honest. Oh, you probably get rid of it because of the next term. So something's missing here, because something's missing definitely, because sinus of, is that correct? The table here, sinus of 2ax, right, divided by 4a. That's what I've done here. Must have gotten something wrong. Let me just Let me just clean that up and then kind of start from scratch a little bit. And say, cool, so we have, I want to solve for these. So we have this integral of, of sine squared of n pi x divided by L dx. So that the way that we solve these, I think I used the wrong, no, that's correct. So it's this x divided by 2 minus, 4a. Yeah, oh no, I think I was doing this correctly, man. So we have these, and so the way you solve this is the integral here will be, so you first say, well, x, right? So x divided by 2 minus sine of 2, like a, which is like n pi divided by L x divided by 4 times n pi. Because you don't have an x here. I'm stupid. That's the mistake I was making. So you don't, you don't have an x here. That's the mistake I was making. So you have these, right? Now, now it's easy. So now you kind of go case one. So x equals L, right? So this gives you L divided by 2 minus, and basically you have this sinus here, which because the x will be L and cancels with this L, and you have a multiple of pi, it's going to be 0. So yeah, divided by, no, nothing. Yeah, 0. That's just it. That's it. And the second case where x equals 0, you're going to have 0 minus, and then you have the same story here. X equals 0, so that is basically 0. So it's just 0. Yeah, okay, so that was way easier. So a squared equals L divided by 2, so a equals square root of L divided by 2. Yeah, that was a pretty straightforward one. I just, it was a bit of a, I think, a mistake. The mistake I made was I kind of put in here instead of just a, like ax, and that's the mistake I did. Okay, so that's clear. Which results in a normalized wave function for particle. Okay, so then you plug that in, and then you have the wave function. And then when you have the wave function, you can plug it in to Schrodinger's equation here, right? Yeah. So you plug it in here, like you do the second derivative of that. Yeah. Do you have to do that again though? Because you know psi, and you know that this is this, so you kind of maybe replace it here, because now you have a, right? Yeah, so you have a, so you kind of have the whole thing here. Then you can just replace that in here and replace that in in here, and then you solve for E. That would be a good exercise. And then you get E equals to these thingy here. So solving for E results in the allowed energies for a particle in the box. So those are the allowed energies. This is an important result that tells us that the energy of a particle is quantized just because of these n's, right? And the lowest possible energy of a particle is not 0. But why does n need to be 1? Like, I thought n can be 0, right? Because that still holds true. Like, because sinus of 0 is 0. If n is 0, that still holds true. That's what's a bit unclear still. right? So if n equals 0, then it means that you're saying that the whole thing is 0. So the sinus of 0 is also 0. So why is n0 not allowed? I don't know. Because if that would be allowed, then actually the lowest possible energy would be 0. Particle can never be at rest because it always has some kinetic energy. So let's look with the Heisenberg uncertainty principle. If the particle had 0 energy, we would know where it was. What does all this mean? The wave function for particle box at the n equals 1 equals 2 energy levels look like these. So the probability of finding a particle in a certain spot in the box is determined by squaring the probability distribution for a particle in the box at n1 and 2 energy levels look like that. Notice the number of nodes. Places where the particle has 0 probability of being located increases with the energy n. Also note that the energy, also that they have 0 probability of being in the middle. That's interesting. That's weird. Also note that as the energy of the particle becomes greater, the quantum mechanical model breaks down as the energy levels get closer together and overlap, forming a continuum. This continuum means the particle is free and can have any energy value or even any position value. At such high energies, the classical mechanical model is applied. Classical mechanical model is applied as the particle behaves more like a continuous wave. Therefore, the particle in the box problem is an example of a wave-particle duality. What does this mean really? So let's read that again. So at a continuum means the particle is free and can have any energy value. I think that's wrong. It's not any energy value. It means any. Because if that keeps getting like this kind of, like bumps like that, then at the end it just ends up being like something like these, which kind of, one would just kind of read as in like, yeah, basically just a straight line, which means that you kind of have the same probability of it being found anywhere. And then it's kind of like a normal wave, isn't it? Like a continuous wave. Therefore, the particle in the box problem is an example of the wave-particle duality. I don't understand why that is an example of the particle-wave duality. Oh, meaning that the system looks like it's a wave, whereas in the quantum case, it looks more like it's a particle because you can locate it in specific positions in the well. That's probably what it means. I think. I'm not so sure that this is what it means. The quantum harmonic oscillator case. So it's a bit of a similar thing, right? So you have the probability. Oh no, that's not the probability. Okay, probability densities. So the higher the energy, the more spread the probability is. I'm not so sure how to interpret that though. It means the probability of it can just be found anywhere, right? So this means that how does this mean that it behaves like a wave? Like this is what I don't understand. But okay, we can think about these later. Questions, draw the wave function for a particle box at n equals 4, 0. Okay, so we could do these questions next time. Draw the probability distribution for particles at n3 energy level. What is the probability of locating particle mass between Calculate the electronic transition energy of acetyladenylate, the stuff that gives you a hangover. What? Using the particle in the box model, assume the aspirin is a box of length. What? What is that supposed to mean? Why an aspirin? Suggest that where along the box transition does like take place. Okay, those are interesting questions. I'm not so sure I grasp them, but I could do them next time. I think I'm happy that at least I understand how the Jesus, what is this thing with notes here? That I understand how this is being solved. Okay, I didn't do the replacing these, the kind of replacement here, but it's just, that's just like manipulating the equation, right? So you would replace, as I said, you will replace these in two spots. So you will replace it, you'll take that as basis, you will replace it here, right? And then here, you either do the second derivative or you just kind of plug in these minus k squared times that. And then it's just a matter of moving things around. I guess the sinuses will cancel, right? So that's kind of obvious because, yeah, they'll be in both sides. We can maybe that's faster than I thought. So let's take a look at it and let's see. Let's convince ourselves that this is true. So you have square root of 2 divided by L, and then you have the sinus of, let's just call these, whatever P, X, right? Just because I suspect that this is going to be, that you'll kind of cross that out. So here you kind of have minus h bar squared times divided by 2, and then this thing here is just a minus, so I guess that becomes a plus k squared sinus of this kind of px thing here. Yeah, k is this whole thing here, by the way. So yeah, so and then it is equal the energy times the same thing, sinus px. So this thing kind of can go away, and so we basically have that E equals k squared times h bar squared divided by 2 times m. Now k is this monster here, right? So k. So this means that energy equals. Oh, so that's neat. So the square cancels out with this one here. So this would be what, 8 times. Oh, but that would be weird because now we are kind of defining. We're kind of defining the. Yeah, no, that's wrong. That's probably the wrong thing to do. So I know that that psi is the square root of 2L times sinus of like n pi Lx, right? So if I do the second derivative of these, is the sinus derivative. So I think the derivative of sinus, right, is cosine, and then and then derivative of cosine is, I think, minus sinus. Yeah, exactly. So that's basically, and so I guess you keep the constant, don't you? I guess you keep the constant. So yeah, you keep always the constants. Okay, cool. So Yeah, so that basically tells you that the second the second derivative is just like minus these, right? Sinus of n pi lx, and then this is kind of multiplied by the whole. Yeah, so now we don't have the k, because that k is just, that's a mistake. So this minus becomes a plus, as we said, and then it's kind of, we multiply by h bar squared divided by 2m, and then that equals to the energy times the same kind of sinus crop, and then so the sinus goes away, so we can basically have that E equals h bar squared 2m times L. No, that's wrong. Isn't it? Isn't it wrong? That's wrong. How do you find that then? Because it's a function of n. Oh, because, yeah. Because the derivative, yeah. I know what I made a mistake. So the derivative of sine ax. So, yeah, so this is, I think you take the a outside, do you? Come on. Yeah, it's a and then, okay, yeah, so you take that a aside, exactly. So that's the mistake that I made. So this means you actually take, and it's a second derivative, so you take that twice out. So you actually have here, like, you have n pi l squared, don't you? Is that anyhow nearby? Yeah, n squared. Yeah. So okay, so that kind of makes sense. Does it? Yeah. Give me a second. So, family stuff, got to pick the little one in the kindergarten. So anyway, but I think it's going somewhere along these lines, right? So this is n squared, blah 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 blah. Yeah, I think that somewhat you square that as well, and then there's L squared in here. Yeah, I don't know how the pi's go away though, but it's something along these lines. Anyway, I'll probably try to fix it next time. I'm gonna go now. Bye bye. That was useful actually. It was actually useful.